So at the end of lecture last time, we briefly reviewed the dissociation of water. So I'm just going to go over a few of the slides we covered at the end, but I'm going to do it kind of quickly. So water is kind of interesting in the sense that two water molecules can come together. One can act as an acid, the other one as a base. So a proton is donated from one to the other to generate the conjugate bases and the conjugate acids shown here. This is hydroxide, and this is the hydronium ion, which is also represented as H+. They basically mean the same thing. And the key thing is that they're formed in equal amounts. And the second key thing is that the equilibrium is shifted way to the left. In fact, the equilibrium constant has a special name. It's called the ion product constant in water. So again, it would just be the concentrations of the products, hydroxide and hydronium ion, divided by water squared, but water is a pure liquid. So pure liquids and pure solids do not enter into the equilibrium constant expression. So it's just this product, which happens to be 1 times 10 to the minus 14. Now this is done by measuring one of these concentrations. They have to be equal, and we can just show you how you can generate the concentrations from the value of the equilibrium constant. So since these are present in equal amounts as pure water, we can just represent each one as x. That would be x squared is equal to 10 to the minus 14th. Then when you take the square root, you get 10 to the minus 7th each. Now, not only does it hold for pure water, but it also holds for for all aqueous solutions at the same temperature at 25 degrees Celsius. So if you have, you've added an acid, or you've added a base, or even an ionic compound, just a salt, this relationship holds. That is, the products here of the concentrations have to equal to 10 to the minus 14th. So for example, if you intentionally added an acid, the hydrogen ion concentration is going to go up, but that simultaneously means that the hydroxide ion concentration goes down, such that the product is equal to 10 to the minus 14. I keep doing that. To calculate the hydronium ion concentration when hydroxide is known, you divide both sides by the hydroxide ion concentration. You get this equation. You plug in 10 to the minus 14th here. You plug in the hydroxide concentration here. And enter these values into your calculator. You'll get that answer. To get the hydroxide ion concentration, you do the same thing, except now you divide by the hydronium ion concentration. So this is how you set this up. So for example, if we know that the hydronium ion concentration is 10 to the minus 5, we take the kW value, 10 to the minus 14th, divided by 10 to the minus 5, and without using your calculator, you just multiply by the ratio 10 to the 5th divided by 10 to the 5th. Now you add the exponents. 5 added to minus 5 is 10 to the 0, or 1. And here we take minus 14 plus 5 is minus 9. So the answer is 1 times 10 to the minus 9th would be the hydroxide ion concentration when the hydronium ion concentration is 10 to the minus 5. Now, all we want to say on this slide is that if you have pure water, these concentrations are identical, and we say that the solution is neutral. It's neither acidic nor basic. But when the hydrogen ion concentration is greater than hydroxide, then we say it's acidic. And when the hydrogen ion concentration is less than hydroxide, we say that it's basic. And here's a sample problem. If the hydrogen ion concentration in blood is 4 times 10 to the minus 8 molar, what is the value of the hydroxide ion concentration? Well, again, you start with this equation, the ion product constant relationship, and in this case, we need to solve for the hydroxide ion concentration. So we divide both sides by H+, plug in our 10 to the minus 14th value. If this is 4 times 10 to the minus 8. Now, for this, you need to put this value into your calculator, and it's important to set up your calculator for scientific notation so that when you divide by 4 times 10 to the minus 8, the operation to divide takes into account this is one number. If you don't do this right, you'll divide by 4, but then over here you'd actually be multiplying by 10 to the minus 8 up here in the numerator. So be sure you set up your calculator correctly. If you're getting a value that's around 2.5 times 10 to the first power, or something like that, then you're not doing this operation correctly. So here we go. We take 10 to the minus 14th divided by 4 times 10 to the minus 8th, and the final result is 2.5 times 10 to the minus 7th. You should verify that value now before moving on. So in this assignment, you're asked to calculate the hydroxide ion concentration given various hydrogen ion concentrations. So shown here is the first one for 10 to the minus 3 molar. We just solve it the way I just showed you. You simply plug your value for Kw in, hydrogen ion concentration is there. We can multiply the numerator and denominator by 10 to the third each if we don't want to use our calculator. Then this would just become 1, and minus 14 plus 3 would give us 10 to the minus 11th. So you should take a moment and try to do all of these. We can try this one as well. So I would just recommend that you go ahead and try these other ones as well. The answers are in your textbook. All right, some of the problems that you're going to encounter on the test are not going to explicitly tell you what the hydrogen ion concentration or hydroxide ion concentration are. Instead, you'll be told that you've got a certain molarity of a given substance in solution. In this case, it's important to recognize that HCl is a strong acid. So if you know that, you know what a strong acid means, it means it 100% dissociates. The equilibrium constant is just enormous. And you form H plus and chloride. And then the second thing you need to remember is molarity means moles per liter. So if I'm counting this as one entity, as 0.1 moles of HCl per liter of solution, then when it fragments into 2 pieces, each one will be 0.1 moles per liter as well. Okay? So if we want to calculate the hydrogen ion concentration for a 0.1 molar HCl solution, we automatically should understand that the hydrogen ion concentration is 0.1 molar. So we solve for hydroxide by taking our Kw value and dividing by H plus. This is 10 to the minus 14th divided by 0.1 is 10 to the minus 13th molar. Then if you're asked for a 0.1 molar sodium hydroxide solution, your starting point, you would know that the hydroxide ion concentration is 0.1 molar. Why? Because sodium hydroxide is an ionic compound and it fragments into 2 pieces, sodium ion and hydroxide. Okay, so here we're asked to calculate the value of both hydronium and hydroxide in a 0.01 molar sodium hydroxide solution. So if you were paying attention to the previous slide, you know automatically that the hydroxide ion concentration is 0.01 molar. Okay, so we know this. We also have this equation. So if we know that, we simply divide both sides by hydroxide to solve for this. Plug in our hydroxide is 0.01 molar, and we get 10 to the minus 12th molar. Actually, this should be, the unit is missing, it should be M. Okay, here we have 4 more problems straight from your book. Given the sodium hydroxide concentration is 0.001 molar, that's the same, we know right away, hydroxide is 10 to the minus 3. So to calculate H+, we use our equation. Right, so we would write this is Kw divided by our hydroxide ion concentration, which is equal to 10 to the minus 14 divided by 10 to the minus 3 and so we get 10 to the minus 11. So if our HCl concentration is 0.001 molar, it's 10 to the minus 3 H plus, then the hydroxide ion concentration, when we solve for it, it's going to be 10 to the minus 11th molar. You can always check this because when you multiply these together, you better get the Kw value, 10 to the minus 14th. When you take 10 to the minus 11th, multiply by 10 to the minus 3, you add the exponents, you get 10 to the minus 14. So it all checks out. The other two you can do in a similar fashion from these starting points. The hydrogen ion is 1.5 molar, now solve for hydroxide. Here you know that it's 0.3 molar in hydroxide ion, so now calculate H plus using this relationship.